That's for convergence, divergence of the summation of the nth root of 2 minus 1 and start from 1 goes to infinity. For this one, I want to use limit comparison test. Let us use limit comparison test. So if you consider two series, one of them is known. For one of them, you already know the behavior, and finding the limit of an divided by bn as n goes to infinity, and it's equal to a positive finite number. Then the convergence and divergence of these two series are the same. Then the convergence and divergence of these series are the same. So for the nth root of, let us take a look, an, the nth root of 2 minus 1. Remember that if you remember the behavior of some basic and elementary functions or parent functions, it makes your life much more easier. So I highly suggest you to take a look at some of the graphs, the parent functions, and remember the behavior of parent functions. So for example, if you consider 2 to power 1 over n or 1 over x as a parent function, the behavior of the graph is very similar to 1 over n. So let me write this guy down for you. It is very useful to remember the behavior of parent functions and their graphs. For example, if you were to graph 1 over x, how do you graph this? What's the visualization look like? F of x equals to 1 over x. If you remember the behavior of the graph behaves like this. Let's just focus on positive part of it, because eventually you're just switching and shifting to positive part for series. So when x is equal to 1, this is what we have. It's equal to 1. When x is equal to a half, it's 2. If x is equal to 2, it becomes a half, and so on. So this is the behavior of this function. What about the x root of 2? All right, or 2 to power 1 over x. The second function that I'm going to graph is g of x is 2 to power 1 over x. All right. So when I plug in, for example, 1 here, I get 2 back. When I plug in 1, I get 2 back. When I plug in 2, I get square root of 2. When I plug in 3, I get the third root of 2, and so on. So if you use a calculator and plot these points, the behavior is very similar to this function, 1 over x. So it's very useful to remember the behavior of the parent functions. It helps you to make comparison a little bit easier. So since the behavior of the graph of 1 over x and 2 to power 1 over x, or the x root of 2, are the same, I'm going to compare this general term with 1 over n. So since the graph of 1 over n and the nth root of 2 have similar behavior, not exactly the same, similar behavior, we are going to use 1 over n and the harmonic series, the summation of 1 over n for comparison. So remember that when you have harmonic function, harmonic series, the series is divergent. Comparison, and note that the summation of 1 over n is divergent, either as a p series when p is equal to 1 or integral test. You can use either of these to check the divergence of the harmonic series. Now let's go back to our comparison test. The limit of, let's call this guy an, and bn is 1 over n. Okay. The limit of the nth root of 2 minus 1 divided by 1 over n as n goes to infinity. This guy is basically the limit of 2 to power 1 over n divided by 1 over n minus 1. Then we take the limit 1 over n as n goes to infinity. So you get 1 minus 1, which is 0, divided by 1 over infinity, which is 0. So you have 0 over 0. Let us apply L'Hopital's rule. This limit is equal to the limit of, under numerator, you have the nth root of 2. So you get, if you remember, when you have a to power x and you take the derivative, you get a to power x times ln of a. So on the numerator, and here if you have u prime a to power u times ln of a in more general form. So the derivative of the nth root of 2 minus 1 divided by the derivative of 1 over n as n goes to infinity. You end up with the limit of, and let me write this guy into the form of the power. So you see we have 1 over n, and we are taking the derivative and divide by 1 over n derivative, which becomes the derivative of 1 over n is negative 1 over n squared times 2 to the power 1 over n times ln of 2 divided by the derivative of 1 over n is again negative 1 over n squared as n goes to infinity. You can cancel out these two. So you're left with limit of 2 to the power 1 over n times ln of 2 as n goes to infinity. But this guy 1 over infinity is 0. 2 to power 0 is equal to 1. So this limit is equal to 1 times ln of 2 or ln of 2. Very good. If you use a calculator, you can approximate ln of 2, but this is a finite positive number. Finite positive number. So, what is your conclusion? By comparison, limit comparison test, since the limit of an divided by bn as n goes to infinity is equal to ln of 2, which is a positive finite number, so the convergence, divergence of the series of the nth root of 2 minus 1 and the series of 1 over n are the same. But since the harmonic series summation of 1 over n is a divergent series, so as the summation of the nth root of 2 minus 1. Let's recap what we did. So our goal was to analyze the convergence and divergence of the nth root of 2 minus 1. What we did, we wanted to try and use the limit comparison test for two series, which one of them is known in behavior. If you find the limit of an divided by bn as n goes to infinity, and if the limit is positive finite number, we can say that, hey, the convergence and divergence of the series are the same. I wanted to compare the nth root of 2 minus 1 with 1 over n. Why is that? Because from elementary calculus or pre-calculus or algebra, I remember the behavior of parent functions. The graph of 1 over x, and x is positive, behaves like this. The graph of the x root of 2 also behaves like this. So they have similar behavior. Since the graph of 1 over n and the nth root of 2 have similar behavior, we're going to use 1 over n and the nth root of 2 minus 1. But the limit of an divided by bn as n goes to infinity is the limit of 0 over 0, which is indeterminate form. When you have indeterminate form, we are interested in using L'Hopital's rule. Indeterminate. Use L'Hopital's rule. When you're using L'Hopital's rule, you have to take the derivative of the numerator, you need to take the derivative of the denominator and simplify as much as you can. But the derivative of a to power u is u prime, a to power u times ln of a, and u in this case is 1 over n. So the derivative of u is negative 1 over n squared, which is up here. Then you copy down 2 to power 1 over n and ln of 2 divided by the derivative of 1 over n, which is negative 1 over n squared. You can cancel out the common factor. You end up with limit of 2 to power 1 over n as n goes to infinity, which is 2 to power 0 or 1 times ln of 2. You end up with the limit, which is ln of 2. You can use a calculator to approximate this number. Indeed, it's a finite positive number. So by limit comparison test, since the limit of an over bn as n goes to infinity is a positive finite number, it means that the convergence and divergence of these two series must be the same. But we already know that this guy is a harmonic series, which is divergent. So the second series must be divergent as well.